In this video, we're going to introduce exponential and logarithmic equations. So when we're solving these types of equations, we're going to use several of the exponential and logarithmic properties that we've discussed before. So remember that we have equivalent exponential and logarithmic forms. So a to the x equals y means the same thing as log base a of y equals x. Remember that your exponential and log functions are inverses of each other. So inputs of the exponential are outputs of the log. Outputs of the exponential are inputs of the log. So that's all this is really saying, is that these are two functions are inverses of each other. So that's exactly what this next part is saying as well, that if I have the function f of x equals a to the x, then its inverse is log base a of x. Since they're inverses of each other, that means if we compose the two functions together, if I do f of f inverse, I should get back to x. So when I do log base a of a to the x, I get out x. And if I do a to the log base a of x, I get out x. Logs undo exponential functions undo logarithmic functions. We have to be a little careful in the second one. Remember that the domain for your log function is 0 to infinity, so this only works if x is greater than 0. This property is true for any x that we want, because we have no domain issues for a to the x. Remember that the log of a product is the sum of the logs. Log of a quotient is the difference of the logs. And if we have the log of x to the r, we can bring the r down in front. All right, so let's see if we can solve equations of this type. So say we want to solve 5 to the 2x minus 3 equals 13. All right, so what we're going to do is we're going to use the equivalent logarithmic form to write this as a logarithmic expression rather than an exponential expression, or an exponential equation, I should say. So basically what I'm doing is I'm taking the log base 5 of both sides. I'm doing the inverse of 5 to a power. Inverse of 5 to a power is the log base 5 of that. So if I apply the log base 5 on both sides, I get just 2x minus 3 on the left-hand side, and then log base 5 of 13 on the right-hand side. So now to solve for x, I just need to add 3 and divide by 2. Notice here in this expression, I've converted log base 5 of 13 to natural log of 13 over natural log of 5, because usually at the end we want to do a decimal approximation. I don't typically have a log base 5 button on my calculator, but I do have a natural log button on my calculator. So here we're using the change of base formula to be able to get an approximation, which in this case is about 2.2968. Let's do another one. Here we have 7 to the 4x plus 1 equals 11 to the 11 to the 5 minus x. Notice that we don't have just a single number on the one side. In the previous slide, we had taken log base 5 because I had a 5 to a power, but I didn't have an x in the other exponent, so doing log base 5 was fine. In this situation, if I do log base 7, I still don't know what log base 7 of 11 is. So what I'll do instead is just do, say, natural log of both sides. I'm going to have a log stuck in there anyway, so I might as well use one of the log functions that I have on my calculator. So I'll take the natural log of both sides. The reason why we're going to take the natural log of both sides is now we can bring down the exponents. We can take that 4x plus 1 down in front of the natural log of 7. We can take that 5 minus x and put it down in front of the natural log of 11. Now we want to solve for x, so we need to gather our x's on one side. So to do that, first we'll distribute our natural log of 7 on the left-hand side. Distribute your natural log of 11 on the right-hand side. Don't be confused by the fact that we've got natural log of 7 and natural log of 11. Those are just numbers. So if this were a 3, you would take the 3 times the 4x and the 3 times the 1. That's all we're doing. It's just that this is a number. It looks complicated, but it's just a number at the end of the day. Gather our x's on one side, so we'll add the x natural log 11 to the left, and we'll subtract, that should be a minus sign here. This should be a minus, not a plus. We'll subtract the natural log of 7 to the right-hand side. So this should say 5 natural log of 11 minus natural log of 7. My apologies. Now the reason why we gathered our x's is because we could factor an x out and then divide. And this is a perfectly acceptable exact answer, except again, this should be a minus in the middle. We should have 5 natural log of 11 minus natural log of 7 over 4 natural log of 7 plus natural log of 11. Now, I believe I have a decimal approximation, and that's not going to be right because I have the wrong number. I have the wrong sign here in the middle, so that's not going to be the right decimal approximation. But you should be able to put this into your calculator and get a decimal approximation. All right, so let's do another example where we're asked to solve an equation with a logarithm rather than an exponential. So I have log base 3 of 5x plus 2 equals 3. Again, we'll write this in the equivalent exponential form. This says that 3 to the third equals 5x plus 2. Or think of it another way, I'm raising each side to 3 to that power. So 3 to this power equals 3 to this power, undoing the log. And then at this point, 3 cubed is 27, subtract the 2, divide by 5. So again, all we're doing is rewriting this in its equivalent exponential form here. Let's do something a little bit more complicated. Let's say we want to solve log base 2 of x plus log base 2 of x minus 3 equals 2. Well, notice that we have a sum of logs with the same base, so we can combine those as multiplication. We can rewrite the left-hand side as log base 2 of x times x minus 3 equals 2. Again, rewrite it in its equivalent exponential form. 2 squared equals the inside. Distribute on the left-hand side, rewrite the right-hand side. We get x squared minus 3x equals 4. This is a quadratic equation, so we need to set it equal to 0. And this one turns out that it factors. And in this case, we get x equals negative 1 or 4. Now, we can't stop here. The reason why we can't stop here is because we need to make sure that these answers that we get work back in the original equation. Okay? In particular, we might get an answer that makes a negative on the inside of the logarithm, and that means that it's not in the domain in the original problem. So for example, when I look at this, here I see log base 2 of x. X has to be greater than 0. Here I see log base 2 of x minus 3, so x actually has to be bigger than 3. So any solution that we get has to be bigger than 3. So in particular, negative 1, not going to work because log base 2 of negative 1 is not defined. So that's an extraneous solution. The reason why we got it is because here, notice when we rewrote the sum, it became a product. When we put in negative 1 in for x and negative 1 in for x minus 3, both of those are negative. When we put it together, we multiplied it, turned it into a positive. So we couldn't plug it in here, but we could plug it in the second step. So that's why we have to go back to the original and check. When we have x equal to 4, though, it works. We get our solution. So the only solution to the original equation turns out to be x equals 4. We throw out the negative 1. Let's do another one like that. Let's look at log base 6 of x plus 3 plus log base 6 of x minus 5 equals log base 6 of 2x plus 6. Just like in the previous example, we can rewrite the left-hand side as the log base 6 of the product of x plus 3 and x minus 5, since we have the sum of the logs. Now notice we have log base 6 of something equals log base 6 of something. Remember, the logarithmic functions are 1 to 1. So that means that if the outputs are the same, the inputs had to be the same. So we can just drop the logs here and get x plus 3 times x minus 5 equals 2x plus 6. Again, we get a quadratic equation. The way we solve all quadratic equations is to set them equal to 0 and either factor or use the quadratic formula. Setting this equal to 0, we get x squared minus 4x minus 21 equals 0. That factors nicely. And we get solutions of x equal to negative 3 and x equal to 7. Again, we need to make sure that both of these solutions work. We notice that if we put a negative 3 in for x, both log base 6 of x plus 3 and log base 6 of 2x plus 6 will be 0. Log base 3 of 0 is undefined. Cannot plug 0 into a logarithmic function. So negative 3 is extraneous. We put in 7, however, we really do get log base 6 of 10 plus log base 6 of 2. Combining those two together, we get log base 6 of 20. We notice that 20 is the same thing as 2 times 7 plus 6. So 7 really does work, and it turns out to be the only solution in this case. Let's do one of these where we can do an application. Let's say we have exponential growth. The current population is 100,000. It's estimated that the population will be 120,000 in 10 years, and it asks when the population will be 250,000. Since we have exponential growth, and since the initial population is 100,000, we can write our population equation as 100,000 times e to some power. So e to a constant times t. Usually we write an exponential growth as an e to a power idea. We know that when we plug in 10, we're supposed to get out 120,000 because it tells us the population in 10 years will be 120,000. That tells us that 100,000 e to the 10k, because we're putting 10 in for t, has to be 120,000. Divide by our 100,000, get e to the 10k equals 1.2. Take the natural log of both sides, we get 10k equals natural log of 1.2, or your k is equal to natural log of 1.2 over 10. You could get a decimal approximation for that, which is about 0.0182. We now want to know when is the population 250,000. So we're looking for the value of t so that p of t will equal 250,000. Well, we know that our p of t now is 100,000 times e to the t times this natural log of 1.2 over 10. That was the k value. I just wrote in the exact value of k rather than put the decimal approximation. Divide both sides by 100,000. Take the natural log of both sides to get rid of the e. Multiply by the reciprocal on the left-hand side and get our t is equal to 10 times the natural log of 2.5 over the natural log of 1.2, or approximately 50.26 years.